So welcome to the video. Today we're going to take a look at how to do an independent t-test on version 31 of SPSS. So we're normally going to use this test when we have a categorical or nominal variable comprised of two levels, so that's an independent variable, and when we have a continuous dependent variable. So for this example, we're going to imagine that we're interested in whether those with or without a family history of Alzheimer's disease do better or worse on a test of memory. So in this column here, we have a number 1 to represent people who do have a history of Alzheimer's in their family, and we have a 2 here to represent people who do not have a history of Alzheimer's in their family. And in this column here, we have their scores on some sort of memory test. So higher score equals better performance on this test. So let's take a look at how to put these data into SPSS. So I'm going to go down to variable view, and then I'll go to this name column here, and then I'll give a name to the independent variable. So I'm going to call this something like family underscore history, and I'm going to use an underscore here because we can't use a space. And then we'll go over to this values column, and we'll click on this little gray box that comes up here, and then we'll go to this plus button, and we'll say that a 1 equals family history, and we'll say that a 2 equals no family history. Then we'll go to OK when it looks like this, and then we can give a name to the dependent variable. So let's call this something like memory score. Next, we can use this measures column here to specify that family history is a nominal variable and that memory score is a scale variable. So these are sometimes referred to as categorical and continuous respectively. Next, we can go to data view, and we can see that the names of those two variables appear at the top of those two columns. So if we go back to this Excel file, we can select the top left bit of data, and then we can go down and select the bottom right bit of data while holding shift, and then if we go to command or control C to copy those data, and then we select the top left cell in SPSS, and we can go to command or control V to paste those data in. Sometimes that doesn't work. That's the case, just go up to edit and then paste, and that should put those data in. And we can see that in this column here we have family history and no family history, whereas in the Excel file we had 1s and 2s in this column. And that's because, of course, we allocated these descriptions to the numbers 1 and 2, and because in this view menu we have value label selected. If we unselect that, we just get the numbers. I tend to prefer to keep it selected. So this test has a couple of assumptions. One is that we have a normal distribution within each of the groups, and that we have homogeneity of variance. And as I've mentioned in this note here, if you find that either of these assumptions is violated, especially the normal distribution assumption, you might consider doing a Mann-Whitney-U test instead, which is the non-parametric equivalent of the independent t-test, and it doesn't assume that the data are normally distributed. So we can check this homogeneity of variance assumption as we run the test, but we should check this normal distribution assumption before running the test. So to do this, we can go to Analyze, and then down to Descriptive Statistics, then over to Explore. Then we can transfer the independent variable to the factor list and the dependent variable to the dependent list. Then we can go to Plots, and then we can tick histogram. I usually untick stem and leaf, and I usually tick normality plots with tests. Then we can go to continue and then to OK. And if we scroll down slightly, we have this tests of normality table. We actually have 2 tests of normality within it. So we have the Kolmogorov-Smirnov test on the left and the Shapiro-Wilk test on the right. We can see that we have 30 people in the family history condition and 30 people in the no family history condition. And we typically apply the Shapiro-Wilk test when we have fewer than 50 people in each condition, and we typically use this test here when we have more than 50 people in each condition. So I'm going to focus on the Shapiro-Wilk test, and we can see here that we have a sig value for family history of 0.720, and as that is above 0.05, it indicates that the data are normally distributed in this condition. Conversely, we have a value of 0.008 for no family history, and as this is below 0.05, it suggests that the data are not normally distributed in this condition. And if we look at the histograms, we can see that they correspond with these values here, because this is telling us that the data are normally distributed in the family condition, in the family history condition, and this is the family history graph. And we can see that we kind of have a sort of normal distribution, bell-shaped thing going on here. However, if we go down here, these data really don't correspond to the symmetrical bell-shaped distribution that you'd expect to see with a normal distribution. So in this case, normally I would switch to doing a Mann-Whitney U-test instead of the independent t-test, but as this is just an example, let's continue with running the test. So to do this, we can go up to Analyze and then down to Compare Means and Proportions, and then we can go across to Independent Samples t-test. We can then transfer the dependent variable to the test variables box, and we can transfer the independent variable to the grouping variable box. We can tick homogeneity or variance test, and we can click on the independent variable here and then on define groups. So as a default, SPSS assumes that you've allocated the numbers 1 and 2 to the different levels of the independent variable, which is accurate in this case because we used the number 1 to represent family history and we used the number 2 to represent no family history. If, for example, you had used 0 and 1 for those two conditions, you could replace 1 and 2 with 0 and 1. But as this is accurate, we can just go to continue and then we can go to OK. So the first thing I'm going to look at is this homogeneity of variance test table and add this sig value here. So we have a sig value of 0.142, and as this is above 0.05, it suggests that the data meet the assumption of homogeneity of variance, which essentially means that the data are spread out to a similar extent in the two groups. And whether or not you see a value above 0.05 here determines which of these two rows in the table above you should look at. So here we have a value above 0.05, so I'm going to focus on this equal variances assumed row. However, if you had a value here below 0.05, you would instead focus on the results in this equal variances not assumed row. So I'm going to look at this significance part of the table and at this top row. You can either look at the one-sided P column or at the two-sided P column, and which you look at is determined by what sort of hypothesis you had. So if you had a one-sided hypothesis, otherwise known as a directional hypothesis, you would have said something like it was hypothesized that those in the family history condition would have significantly lower memory scores than those in the no family history condition. So you're predicting which group is going to have the higher or lower value. Conversely, if you had a non-directional or two-sided hypothesis, it would be something like it was predicted that there would be a significant difference between the two conditions. So you're not predicting which condition would have the higher or lower memory score. So let's imagine that we had a one-sided hypothesis, and we can see here that we have a p-value of less than 0.001. So as this is less than 0.05, we know that we have a significant difference between the groups in terms of their memory scores. And if we look at this group statistics table and at this family history row, we can see that we have a mean value of about 62. And if we look at the no family history row, we can see that we have a mean value of about 77. So the memory scores in the no family history condition were higher than they were in the family history condition. So that's essentially how we interpret the results of the test, but let's now take a look at how we can report those results. So I started off just by saying what we did the test for. So I've said that an independent samples t-test was conducted to compare memory scores among those with and without a family history of Alzheimer's. Then I've reported the normality test results. So I've said that Shapiro-Wilk tests indicated that the data were normally distributed in the family history group, but not in the no family history group. And then I've inserted all of these statistics. So here we have W equals 0.98. So that's coming from this test of normality table, and we're looking at the family history row. And in the statistic column in the Shapiro-Wilk part of the table, we have this value here of 0.976. So if we round that to two decimal places, we get 0.98, and we have a degrees of freedom of 30, and we have a sig value of 0.720, and that's what we have here. So there's the degrees of freedom, and there's the P or sig value. And then I've just done the same thing for the no family history condition. And those stats are just coming from this part of the table here in this bottom row. Next, I've said that Levine's test indicated that the assumption of homogeneity of variance was met, and then I've inserted an F value and a P value. So the F value is 2.22 and the P value is 0.142, and we're getting those values from this homogeneity of variance test table, and we have an F value of 2.22 and a sig value or a P value of 0.142. And then next we get on to reporting the results of the t-test itself. So I've said that memory scores were significantly higher in the no family history group than in the family history group. And we've reported these means and standard deviations. So these are those for the no family history group. So if we look at this group statistics table and the no family history row, we have a mean of 77.37 rounded to 2 decimal places. And that's what we have here. And we have a standard deviation of 8.70. And so that's coming from this bit here. And we've just rounded this value 2 decimal places, and then we've just reported this value here and this value here for the family history group here. Next we have the results of the t-test itself. So we've said that t equals minus 6.98. So I was focusing on this top row of this independent samples test table where we have a t-value of minus 6.98 rounded to 2 decimal places. We have a degrees of freedom value of 58, and we have a p-value of less than 0.001, and so we have that degrees of freedom value here in brackets, and we have that p-value over here. And the final thing I've reported is this Cohen's d-value of minus 1.80. So I've said the effect size was large, and I'm getting that value from this independent samples effect sizes table and from this Cohen's d row and this point estimate column where we have this value here of minus 1.80 rounded to 2 decimal places. I've described that as a large effect size, and that's based on these criteria described here. So typically Cohen's d values between 0 and 0.2 represent very small effects. Those between 0.2 and 0.5 represent small effects. Those between 0.5 and 0.8 represent medium effects, and those above 0.8 represent large effects. And as mentioned in this note here, the same criteria apply if we're looking at negative values. So here we have a negative value that is greater than negative 0.8, which is why I've described this as a large effect. So that's about it for the independent t-test on version 31 of SPSS. I hope that was helpful. If you have any questions, just let me know in the comments and I'll try to get back to you. Thank you for watching, and I'll see you next time.